I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class, for these students. Just ask you just bless our work today. Help us to just wrap up any questions that remain for test 2, and just help the students to just use their time wisely this weekend and to study anything that remains and just to do their best, Lord, each day for your glory. In your name I pray, Lord Jesus. Amen. Okay. I guess I'll do things backwards in here. Let's talk about the test. So I usually talk about the solution to mission 2, but here is test 2 from last spring. So this is approximately like your test that you're going to take Monday, okay? Now, not exactly the same, but similar in difficulty and content, I would say. So let's just run through this, and let me get my pointer out. Oh man, come on. What happened? I had, bummer. Oh, wait a minute. Some of these aren't very, these marker caps are not sticking together very well. Drat. Finally. Haha. What's that? Yeah, I think this is test 2. Are we test 2, right?
Yeah.
Okay, yeah.
Are we able to access this through Canvas?
No. But I can put it up there if you like. Okay, I don't think I posted it yet, but I can. And of course, I'll post this video, so there's that. But all right, so let me just go through this really quick. That's a volcano. Volcano function, that one. That is an upside down square root. That must be that one. That's a cube root. It's got to be that one. Absolute value, it's got to be that one. There you go. So now, of course, I could spice it up and give you like 2 cube roots, so you'd actually have to think about the transformations too, but you know. The start of mission 2 was about simplifying rational functions, right? So here's a couple problems like that. To clear out the denominator, we multiply by x plus 1, top and bottom, and simplify. This one, if you factor that, multiply through, the x plus 1 cancels, the x plus 2 cancels, leaving you x plus 2 and x plus 1 respective. Don't forget the parentheses. Parentheses are your friend. And then the x's be canceling. 2 minus 1, 1. Yep. I feel like that might have been a homework problem. Problem 3, moving on, rational inequalities. So here you want to identify all your critical numbers, which in this case is minus 3 from the top, a 4 and an 8. Put them in order, plug in number, get a plus. Multiplicity of each one of these is 1, so you flip signs each time, plus to minus, minus to plus, plus to minus. And yeah. And then I'm looking for positive. So I got positive between minus 3 and 4, and then also from 8 to infinity. And I need to exclude where we have division by 0. So I do not include 4, and I do not include 8. But on the other hand, minus 3 is fine, because that just gives us an expression of 0, right? Value of 0. So that's how you do that. So that's actually pretty much the same as test 1, right? Test 1, we had the nonlinear inequalities, but there wasn't rational functions. They were just polynomials. It's the same song and dance, though. Here, cross multiply, put all your x's on one side and all the numbers on the other, solved. Right? There's nothing really to check. I mean, like, if you do the steps correctly, it's going to work, right? Now you can go back and check your work. If I plug 4 back up in here, I get 3 times 4, which is 12. 12 plus 2 is 14. What's 4 plus 3? 14 divided by 7? Okay, good. Right, it worked. Yay! There was a request that I not put this kind of problem on the on test 2 in the other section, and I told them that you know, I did it last semester, so I am a creature of habit. So it's probably going to be there. right? So you need to work on this if you're not super good on it yet. And the rules are basically simple, that you need to remember, like, square root is the half power, cube root is the third power, and we just use laws of exponents and simplify, and, you know, c is a half, 5 halves for this one, a is 2, b is minus 1. Problem 6, I think this one you already experienced on quiz 6 and 7, right? I actually recycled this problem for you guys on like the last quiz, I think. So I'll skip over that one. Just to reemphasize the concept, though, before I go on, when is there a hole in the graph? When something cancels, right? When you have a factor in the numerator and the denominator, they're shared, then there can be a hole in the graph. Problem 4 got a lot of people last semester in the spring. This took many points from, well, not a lot of points, but it took points from some people for various reasons. Now, this one is a little bit unfriendly because f of 1 doesn't line up anywhere nice. Like, this is the graph of f here, so f of 1 is there-ish. So I put 1.6. Now, I try to make things work out so they're not like ugly like that, but sometimes it happens. If it happens, you just do your best, all right? And some people were like, well, what if I said like 1.5? And be like, well, that'd be fine. And there's like, well, what if I said 1.4? I was like, well, then I take points off. So, okay, that's a joke. But if you're close, you kind of see it's bigger than 1.5, right? I mean, can we agree? I don't know. I mean, it's debatable. Anyway, I can tell if you're doing something approximately correct there or not, all right? And anyway, so 1.6 times, so this is the product of f and g, so it's f of 1 times g of 1, which is this, which is that. Now this is composite. Notice the little circle there, that's composition. F composed with g is f of g of minus 1. Now g here is not the graph. G is this formula. G of minus 1, well, minus 1 plus 3 is 2. F of 2, well, look at the graph. 2, f of 2 is actually equal to 2. So the answer is 2. Now, g of f of 2, well, f of 2 was, as we just said, 2. And so g of 2, well, I go back to my formula, 2 plus 3, 5. So there's also, as you can see, a case-wise defined function. Find f of 2, find f of 0. These are not hard. You just need to do what? Make sure you're following the instructions, right? There are 2 cases. Figure out which case you're in. Use the formula for the case. Now, I usually do at least ask one graph on the test. One graph to do as careful as you can. And here it is. What's that? Was it what? Oh, right. So that was also true for them. So, because I use the same mission for them. So they should have all got this exactly right, right? Yeah. Yeah. Did they? No. No. They did not. Did I let them have a sheet of notes? I did. I don't know. I've been thinking, if I did the tests for the students, what if I just did one test and then made like 40 copies? I could easily improve the S rates in all my classes. You know? That's like the next thing, like the best pedagogy would be just doing the tests for the students. It would be safer. Yeah. Sometimes I feel like that's what's happening online, but like my wife teaches online, and like some students ask so many questions. Like, I wonder, do they do any homework? Like, she had one student send her like 30 questions. 30. And you might be like, over the course of an 8-week term? No. One day. One day. The thing is, she answers them. I'm like, no. You should just put your foot down and be like, I'm sorry, but I have a 3-question-a-day limit. Something like that, you know? Would that be reasonable? What do you guys think? Yeah, right? All right. I need to talk to her boss and try to get that to be department policy so students start doing their own course rather than my wife. We are grateful for her job. But anyway, let's see here. Oh, yeah, this problem. So I think this one, no holes, right? Why are there no holes? Yeah, there's nothing to cancel out top and bottom. So on the other hand, this one does have an x-intercept because of the x upstairs, right? So that means it goes through 0 at 0 because of this guy, right? And the plus and minus 4, those are vertical asymptotes. Like that means that the graph doesn't cross there, but it gets really big or in the positive or negative sense at those vertical asymptotes. I draw a sign chart to guide me. So it's positive if I put in like, 10 or whatever. And then each factor has multiplicity 1 again, so we go plus, minus, plus, minus. And then the other thing to think about here is the y asymptote, the horizontal asymptote, which is y equals to 0. Why? Can you guys tell me why the y asymptote's 0 here? The horizontal asymptote 0? We had two cases, right? Either the horizontal asymptote is y equal to 0, in which case? In the case that the denominator has a larger degree than the numerator, or what's the other case? The horizontal asymptote is y equals to a constant, right? Because the degree of the top and the bottom match. Now, of course, this one, I ask you to find the horizontal asymptote of 1 over x minus 3 plus 2. So that kind of falls outside the scope of my theorem, doesn't it? But if you think about that one, think about putting in a large number, what happens? If I put in 1,000,000, all that matters is the 2, right? So this goes to 2 for large values of x, in either the negative or positive direction. Of course, you could make a common denominator. If you did that, you'd end up with like 2x minus 5 over x minus 3, and then the ratio of the leading coefficients would be 2 and 1, and you get y equals 2. You could do it that way if you wanted, but you don't need to. All right, here was a long division problem. I said evaluate f of 1 and f of minus 1. That was so that they would see that the value of the function was 0, which tells me by the factor theorem I've got a factor of x minus 1 and x plus 1 respective. We would rather do one division than two. So I multiply the factors so I can divide x squared minus 1 into that. All right. And then what? And then that gives me the cofactor x squared plus x minus 12. But that factors into x plus 4 times x minus 3. So there you go. Well, it says to factor completely. So you get partial credit. If you just got to here, you'd get partial credit. I mean, I would say that's probably like minus 2 or 3 out of 15 if you didn't factor the last step. Most of the credit's for the long division here. This one is a complex factor of f of minus 3 plus I equal to 0. So that tells me I've got an x plus 3 plus 1, x plus 3 squared plus 1, which multiplies out like that. So I divide that into my quartic, and of course I get a remainder of 0. If I didn't, that would be bad news for Pastor Chuck. He wouldn't be very reliable, would he? Or we would have made a mistake in our long division, also possible. Hopefully that doesn't happen. Anyway, so we get this, and then of course, again, we can factor, and there you go. I know I can't factor the x squared plus 6x plus 10 because that came from what? That came from the complex 0, right, which corresponds to a prime quadratic. This one here, we're crossing at minus 6, bouncing at minus 2, and crossing at 4. So to get a crossing, I just need a linear factor, x plus 6, x minus 4. Of course, I could also use x plus 6 cubed or x minus 4 to the 5th power. It would still give me a crossing, but then it wouldn't be the lowest degree, right? So if I want the lowest degree possible, I just use a single copy of it. And the lowest degree, which will bounce, is an x plus 2 squared there. Now, after all of that, it doesn't fix the 1/2 I have a variable out here, a, which I can adjust, I can play with, to fit the other piece of data here, which is that f of 0 is minus 48. So I plug in 0, I get minus 48, and then I solve for a and get a half. There was a problem like this in the homework, yeah? I think so. Radical equations, how do we solve radical equations? We isolate the radical and square, but then you got to do what? You got to check your answers because you could have an extraneous solution. And again, if it's got radical square roots, we do what to get rid of square roots? We square.
Do we have to say it's extraneous?
Yeah, I want you to box the answer, so if you don't box the answer and you just leave both, I'll count it off. Yeah. You don't actually have to write extraneous, but I just cross it out, yeah. Oh yeah, well, I guess that was it. Now, listen, I'm not saying that the test is exactly like this. Like, there are some other mission problems that we did that were, I think, test-worthy. Like, what's another one? How about this? One where I say solve for y and tell me whether it's a function, whether it's a function or not. Like, that's a decent question. Let's go back to that. These ones, right? Like this is a decent question for the test as well. It just didn't make it, you know? I had a longer test and I go, I didn't like this one or that one or the other one. And I chopped it down to what I had. But so that test I just showed you gives you a reasonable length, but I'm not saying it's exactly those questions, okay? So you should study the mission, make sure you know how to do the different problems. Now there's one exception I think that's kind of obvious, which is which one? The Desmos one, right? You don't have Desmos on the test. I can't very well ask you to graph stuff in Desmos and look at it, right? That'd be silly. But this one here, I solve for y, and I get plus or minus, right? That means it's not a single function of y, therefore not a function. On the flip side, you could look at it vertically, fails the vertical line test, not a function, right? In contrast, the next part B and part C, those did solve nicely for one single function of y, because the cube root doesn't have the square root property, right? When you take the cube root of an equation, you're not losing solutions. Likewise, when you cube an equation, you're not losing solutions because you don't squash minuses. Like when you square an equation, you're squashing minuses. So you might be losing things, or you might be gaining things, depending on how you're looking at it. Anyway, cube root of that, we got a single formula for y, so y is a function of x. Likewise, this one, I can solve for y, single function. In fact, that's a line, isn't it? So this one, that's a kind of weird equation for a line, isn't it? A little bit. It turns out it's that. Technically speaking, it's probably like a line missing a point or something stupid, but anyway. It's probably like a line with a hole in the graph, if I was to think about it more carefully. Let's not do that. Those are kind of neat. How about domain? How do you think about domain? Domain, you got to avoid what? Division by 0. And if you got a square root, you need to make sure what's going into it is non-negative, right? So this one was automatically non-negative because when I complete the square, it's greater than or equal to 11, so there's no trouble anywhere. So the domain of that was everything. In contrast, this guy, I need to make a sign chart and figure out, oh, well, this is only non-negative between minus 3 and 3 inclusive. Right, so that was its domain. Anyway, I'm going to shut up. Do you guys have any particular questions about problem? I can keep poking around in mission 2 and talking about stuff, but if you guys have a specific question you'd like me to address, we could do it.
Can you explain the last graph, like the last one?
Oh, like the last problem on the mission?
Yeah.
Like 72?
Yeah.
Sure. Yeah, this one's got a little bit to it. I think this is actually easier in terms of the graphing. I think this is easier than the couple problems before it, because this one doesn't have any holes. I just think holes are hard, personally. But this one, I need to make a common denominator is the first thing, okay? So like, I multiply this one by x minus 3. I multiply that one by x plus 4. So I have a common x plus 4, x minus 3 denominator. And then, since that's missing both of them, I multiply by both of them. Now I've got a common denominator. And then I just multiply it out and collect stuff. I eventually get to this. And I looked at that and I thought, I thought, do I want to factor it? I don't want to factor it. I feel like it's prime, so if I have a suspicion something's prime, then I fall back on the discriminant test. The discriminant test is just to check b squared minus 4ac. If that thing's negative, that means we can't factor it. Remember this? So if I look at this, I've got multiplying the minus through. I've got a equals minus 2, b equals 7, c equals minus 24. So if I plug that into my b squared minus 4ac, I get 49 minus this number, which is bigger than 49. Therefore, that's less than 0, which shows me that it's prime. This is wonderful because that means that this has no zeros. The numerator has no zeros. Therefore, all of the critical numbers are just staring back at you right in the denominator. Minus 4 and 3. Those are your only critical numbers. Yay. So the sign chart looks like this. Minus 4 and 3 here. And, oh, the other thing is, what's the horizontal asymptote before I go down? Is it 0 or is it a constant that's non-zero? What do you think? For this one, what would the horizontal asymptote be? If they're equal to degree, we're supposed to take the ratio of the leading coefficients, right? Leading coefficients upstairs, minus 2. What's the leading coefficient downstairs? You got to multiply, yeah, it's 1. You got to multiply it out to see it, right? This is x squared plus x minus 12. If we multiply it out, so that means the leading coefficient is 1. So the horizontal asymptote is minus 2 over 1, because that's the ratio of the leading coefficients. And I need to know horizontal asymptote and I need to know vertical asymptote in order to graph. So the vertical asymptotes are at minus 4 and 3, like these, and like that. And the horizontal asymptote's down here at minus 2, like that. And then I graph according to the sign chart. I got to be going to minus infinity on this side of the vertical asymptote. I got to tend towards the horizontal asymptote long term. Here, I can't cross the x-axis because I've got no x-intercept. So it has to bend back up again like that, forced to do that. And again, it's bending back towards the horizontal asymptote eventually, but it's got to be negative, so it's got to go to minus infinity on that side of the vertical asymptote. So vertical asymptote, graph always has to go to plus or minus infinity on either side of it, which when it goes to depends on the sign chart. Again, I think this one's actually, I mean, the algebra is a little bit tough at the start of it, but the graphing itself isn't too bad. This one here is a little bit trickier in some sense because of the hole in the graph. So here, you know, I've got a common x plus 4. I cancel that. This gives me the reduced function. So I can see, and then my method is this, guys. I graph the reduced function and then add the whole. So the reduced function only has one critical number. What is it? 4. In fact, I don't even think I drew the sign chart here, did I? How did I know how to graph y equals 1 over x minus 4? How did I graph that? I use transformations of graphs, right? Because I know that this is one of my basic graphs, right? Like this. And if I shift 4, it's like this, right? So it's just take the reciprocal graph and shift 4 units to the right. I don't even need sign charts and all that jazz. I just know this. This is just basic, from my basic list of graphs that I know. I can just write that down. But anyway, once you have that, and I mean, just to double check things, how did I know that the y equals 0 was the horizontal asymptote? Because the degree of the denominator is bigger than the degree of the numerator. So y equals 0 is my horizontal asymptote. Division by 0 at 4. All right, just checking things. Now where does the whole go? Well, the whole goes at minus 4. But where does it go in terms of its coordinate? Well, that's what you use the reduced function for. Plug in the coordinate for the whole, namely minus 4, into the reduced function formula, and you get minus 1 over 8. So that's where the whole actually is. Like that. We had a problem like this on the quiz, right? Remember? Problem 68, similar animal, but this one is, I think this one's easier, the easiest so far today that we've looked at of these sort. There's no hole, right? And there's no algebra, it's just there waiting for you to graph it. So the critical number is 2. The other critical number is -3. I make my sign chart, right? And then I graph, so I've got a vertical asymptote with the factor in the denominator. I've got an x-intercept with the factor in the numerator. And then the other, well, slightly tricky thing is that the ratio of the leading coefficients here is 1/1, which is y = 1, my horizontal asymptote. And then I graph. Any questions? No? Let's see here. This one's slightly different. This problem 65, a little bit, yeah.
I wanted to ask a little more.
Oh, go for it. Which would?
The case lines that we had to turn it into a case wise.
Oh, this one. Problem 51. Yeah, problem 51 is a little sneaky. The thing is, the square root of something squared is actually a case-wise defined function in disguise. Reason for that is that this is the absolute value of x minus 1. Which then means that the two cases are this and that. Which then, depending on whether you're less than 1 or greater than 1, either gives you this or that, which simplify, of course, to -1 and 1. Yeah.
Is there multiple different formulas that you could get the same answer with, or does it have to be those two?
What do you mean?
Like, could you have x minus 1 over x minus 1, all of that minus 2? Is that? And then have the other be x minus 1 over x minus 1?
I think if you have x minus 1 over x minus 1 minus 2, that's equal to -1. And this one is equal to 1. So your formula is simplified to what I have. It's the same. But of course, you want to simplify. So yeah, I mean, that's the same answer. But I like my boxed answer more, right? And of course, with this kind of thing, if you don't know what to do, experiment. Just try plugging in a number. What happens when you plug in like 5 into this? What do you get? 5 minus 1, 4, right? 5 minus 1, 4. 4 squared, 16. Square root of 16, 4. 4 over 4, 1, right? Try plugging in like 0 into it. What do you get? -1 over the square root of -1 squared. That's -1 over 1, which is -1. And if you just keep experimenting, you just plug in some numbers, you'll quickly learn that the only thing you ever get out from this is 1 or -1. Which then gives you an idea about the kind of algebra that you maybe should be trying to investigate. Admittedly, this is a very hard problem unless you happen to notice this. So, which you guys did a different way. I'm not sure. I'm curious. How did you guys do it?
I just kind of tried separating, and then I just like put it in my calculator and experimented with my math.
Oh, okay. Ah, I see. So you found something in your graphing calculator that matched the graph of that? Oh, cool. Oh, neat. Okay. Ah, okay. Very cool. Once upon a time I would have done that. Does that answer your question about this? I mean, in the other case-wise question, you probably don't really have question. I mean, maybe, I don't know. This one here, x squared plus 3 for x less than 3, x less than 1 rather, x cubed if x is greater than 1. So this is like the x squared plus 3 graph up to that point, and then the x cubed graph takes over after that. So that's kind of a nice problem. If a student can answer this question, they pretty well understand case-wise defined functions truthfully. And a good bit of graphing, I would say, as well here, actually. Oh, a couple warnings before I forget. There's 2 mistakes in the solution. Mistake number 1. This is incorrect. That should be what? This is x over x, the cube root of x is actually x to the positive 2/3, right? It should be x to the positive 2/3. See, if I have x over the cube root of x, that is equal to x to the 1 over x to the 1/3, which is equal to x to the 1 minus 1/3, also known as x to the 2/3. So we have x to the 2/3 equals to pi, which then gives me x to the 2/3 raised to the 3/2 is pi to the 3/2, also known as x equals to pi to the 3/2. There is the actual answer to this problem, as opposed to that nonsense. All right, so what I have, and I'm not going to have time to fix this, guys, so I'm just warning you, as you're studying, please be warned, there's a mistake in the key right here, okay? There's the solution. And then the other mistake that I know of, and if you guys find other mistakes in the key as you're studying, just email me, and I'll tell you if you're right or wrong. Ooh, I like problem 48. Isn't that one neat? You're like, you have a strange sense of what's neat. It's fine. Where is the other mistake? Oh, right at the start, the first problem. Typical of me, make my mistake right in the first part of the first problem. So you guys tell me the mistake. Right, yeah, exactly. When I combined the fractions, I failed, because 5/6 does not become 3/6 when you do that. So somehow I was thinking to myself, multiply by 3. So 3, what? No, 3 times 5 is 15. That should be a 15, as I have over there. So that's the other mistake that I know of. So, sorry about that, but you have been warned. Anyway, so I think that's it for today, because I think you guys are out of questions, so we'll stop here.